we are going to discuss the working principle of another very popular network, and that is called actually the counter-propagation neural network, and in short, so this is known as the CPNN. Now, before I start with this particular network, let me tell you the purpose of developing this particular network. The purpose is once again to model the input output relationship of a process as accurately as possible. Now, here this was proposed in the year 1987 by Robert Nielsen. Now, this network consists of in fact 3 layers. One is called the input layer. We have got the unsupervised coherent network or the coherent layer, and we have got actually a supervised layer, that is called, we follow the principle of Grossberg learning, and we have got one teachable output layer, and this particular layer is going to perform the Grossberg learning, which is nothing but a supervised learning. So, in this network we are going to consider both supervised as well as unsupervised learning. Now, let us see how does it work. Now, construction wise if you see, so this particular network consists of 2 models. One is called the in star model and another is called the out star model. Now, this in star model actually consists of input and the coherent layer, and the out star model consists of the coherent and the output layer. Now, we are going to discuss in details what is happening in the in star model and what is happening in the out star model. Now, let us see actually what is happening there, but before that let me just tell you a few facts that this particular CPNN, that is the counter propagation network, is found to be faster than the multi-layered feed forward network, and here we do not use the concept of the back propagation algorithm. So, the chance of its the solution for getting trapped in the local minima is actually nil, and this CPNN, if you see the performance, that the accuracy in prediction, so it could be little bit inferior compared to your multi-layered feed forward network, but it is computationally faster compared to your multi-layered feed forward network. Now, if you see the literature, the CPNN could be either a full CPNN or it could be a forward only CPNN. So, we are going to discuss the working principle of both full CPNN as well as the forward only CPNN. Now, let me first concentrate on the full CPNN and how does it work. Let us see its working principle. Now, this is actually the schematic view of the full CPNN, and if you see construction wise, it has got 2 input layers. So, I have got one input layer here. So, one input layer here, I have got another input layer here, then we have got 2 output layer. So, this is one output layer, another output layer, and we have got actually a common hidden layer, and this hidden layer is denoted by this. So, we have got 2 input layers, 2 output layers and one hidden layer. Now, the in star model consists of, as I told, the input layers and this particular hidden layer. So, this is actually what we mean by the in star model, and the out star model consists of the hidden layer and the output layer. So, this is nothing but is the out star model, and here actually we take the help of some connecting weights like your U, then comes V, W and S, and these connecting weights are lying in the normalized scale. Generally, we consider 0 to 1 or from -1 to +1. Now, here the purpose of this particular model is to establish the relationship between the inputs and the outputs, and supposing that I have got a process, and this process I am just going to model, and this process is having say m number of your the inputs x 1, x I up to say x m. So, this is your x 1, then comes your x I, and then comes your x m. So, we have got m number of inputs, and this process is having say small n number of outputs denoted by y 1, y k, y n. So, we have got your y 1, then comes your y k, and the last one is say your y n. So, we have got n number of outputs. So, this particular process I am just going to model with the help of your full CPNN. Now, here actually what we will have to do is, as we have already mentioned, that we will have to implement the Cohen network first, and we will have to find out who could be the winner of this particular lying in the hidden layer, and then we will have to go for some sort of supervised learning also, that is your the gross bug learning. And let us see how does it work. So, let me concentrate first on this particular the in-star model, and I have already mentioned that in the in-star model we consider the two input layers and the hidden layer. Now, here, so these two input layers we are drawing in a slightly different fashion. For example, say this is one input layer, this is another input layer, and this is actually your the hidden layer. So, from this particular x, so I am just moving towards the hidden, and from this particular y, once again we are moving towards the hidden. You can see the direction of arrow. So, these are coming from the both the sides, and this is nothing but is your the hidden layer. And on the hidden layer actually we have got small p number of neurons, and as I told, our task will be out of this small your p number of neurons just to identify who could be the winner. Now, the connecting weights between your x input layer and the hidden layer is nothing but u, and the connecting weight between your y input layer and the hidden layer is nothing but is your the v, and this is actually the construction of this your the in-star model. Now, let us see what we do in in-star model. So, we generate the connecting weights, that is u and v, in the range of say 0 to 1, and we consider some learning rate. For example, say the alpha is the learning rate between x input layer and the hidden layer, and beta is the learning rate between the y input layer and the hidden layer. Now, this alpha and beta will lie in a range of say 0 to 1. So, they are going to lie in the range of your 0 to 1, and those particular your connecting weights this learning rate will vary in this particular the range. Now, here as I mentioned that we are going to use the Cohen's self organizing map just to find out like who could be the winner lying in this hidden layer. Now, if you see the way this particular the winner is declared is as follows. So, we try to find out the Euclidean distance between your this Euclidean distance, that is d j. Now, what is d j? So, this is nothing but the square root summation I equals to 1 to small m x I minus u I j square plus summation k equals to 1 to n y k minus v k j square. Now, if you remember, so we have got small m number of your the inputs x inputs and your small n number of your y inputs, and this u I j is nothing but your the connecting weight, and V k j is nothing but the connecting weight, and here j varies from 1 to p. So, p is nothing but the total number of neurons lying in the hidden layer. So, for each of these particular the hidden neurons, we try to find out what is this d values, and then we compare that which hidden neuron is going to give the minimum d value, that will be declared actually as the winner. Now, here the connecting weights, that is u I j, will have to update using this particular the rule, that u I j updated is nothing but u I j previous plus alpha multiplied by x I minus u I j previous. Now, here this alpha is nothing but the learning rate lying in the range of 0 to 1. Now, here, so this particular I is nothing but 1 to up to your small m, and as I have already mentioned. So, the small m is nothing but the number of x inputs. Now, V k j, so this particular connecting weight, how to update? So, V k j updated is nothing but your V k j previous plus beta into y k minus V k j previous. Now, this particular beta is once again the learning rate. Now, once that particular your process is over, now we are in a position to declare that who could be the winner lying on the hidden layer, and that completes actually the iteration, one iteration of instar training. Now, actually we will have to go for some sort of the outstar model. Now, if you see the outstar model will look like this, and as I told that we have already got the winner. Supposing that your z j is nothing but the winner, and this particular winner is lying on the hidden layer. Now, if you see the connecting weights between this winner lying on the hidden layer and your this x star is denoted by actually your w, and the connecting weight between your the winner hidden neuron and your y star, that is your output layer. So, this particular connecting weight is denoted by is your S, and we can assume or we can generate the values of the connecting weights initially at random, and we can update also. Now, how to update, that we are going to discuss. Now, here if you see, so this I have already mentioned here. For example, z j is the winner, connecting weights are lying between 0 and 1, and gamma is actually the learning rate between z j and x star output layer, and delta is actually your the output the learning rate between z j and y star output layer. Now, if you just see, so z j and x star, if between the z j and x star, if you see, so between your z j and x star, if you see, so here we have got your your learning rate, and here we have got another learning rate. Now, these particular learning rates actually we will have to assign some numerical values, and their values will lie between 0 and 1. Now, let us see how to carry out. So, this particular the training of the outstar model, and as I told that we are going to use the Grossberg's learning rule for updating of the connecting weights, that is your W and S. Now, according to your this Grossberg learning rule, so W j I updated is nothing but W j I previous plus gamma into x I minus W j I previous, and here I varies from 1 to up to m. Then S j k updated is nothing but S j k previous plus delta multiplied by your y k minus SJK previous. So, by following this actually we can update the connecting weights, and once we have updated, then at the end we can take the decision that xi star is equals to ji updated and yk star is nothing but is your SJK updated, and it completes actually one iteration of this outstart training. And once you have completed your this instart training and the outstart training, and now we are in a position to find out what should be the output for a set of inputs. Now, if you see like how to implement this, now to implement this actually we are going to solve one numerical example, but before that let me try to concentrate on another possibility of this CPNN, that is your the forward only CPNN. Now, till now we have considered, we have discussed the full CPNN, where we consider there are 2 input layers, 2 output layers and 1 hidden layer. Now, for this forward only CPNN it is simpler in fact. Now, here we consider only one output layer, only one input layer. So, we consider in fact your only one input layer and only one output layer, and in between we have got say one hidden layer. Now, if you see the construction of this forward only CPNN, it looks like this. Say we have got one input layer consisting of small m number of neurons like x 1, x I up to x m. So, this is nothing but the input layer, and we have got small n number of your the neurons on the output layer, and which indicates actually y 1, y k and y n, and this is your the hidden layer having p number of neurons, and in between your this input layer and the hidden layer. So, we have got the instar model, and in between the hidden and the output we have got this particular your outstar model. The working principle is exactly the same. So, what you will have to do is we will have to pass the set of inputs and these connecting weights like your u and v we will have to go on updating, and what you can do is we can use the coherent network or the coherent that is unsupervised training sort of thing, just to find out who could be the winner, and after that we can take the help of your the gross-work learning, and once again we can use both supervised as well as unsupervised learning just to determine like what should be the set of outputs corresponding to your these particular your inputs. Now, as we have already mentioned that this particular CPNN can be used to model input output relationship of any engineering process. Now, here if we compare the performance of this particular CPNN with back propagation neural network or multi-layered feed forward network or radial basis function network, there is a possibility that we may not get so much accuracy in this particular the CPNN. But CPNN actually there is one advantage, because we do not use the back propagation algorithm or the gradient based algorithm. So, the chance of the solutions for getting trapped into the local minima is nil. So, there is no such chance of local minima problem, and that is why actually many people prefer so this particular CPNN even compared to multi-layered feed forward network. Thank you.